Now, the first factor is that K1 is greater than K2, K2 is greater than K3, K3 would be greater than K4, and so on and so on and so on. And ideally, this is just a purely statistical phenomenon. When you have the first metal there, you've got 6 waters. You're going to replace one of those 6 waters by a ligand, so you've got 6 chances. Then you move on to the next stability constant, which would be K2. Well, there's already one of those positions is filled by a ligand, so now that incoming ligand can only replace one of 5 waters, and then one of 4 waters and one of 3 waters. So as the chances go down, so does the successive stability constant. Okay, that's what you would expect from statistics. And indeed, if we plot out this thing now, a lot of these reactions in this are starting to get rather yucky, okay? But keeping it nice and general, we have a metal ion with so many numbers of waters on it. In other words, only waters bonded to the metal ion. We're going to react it up with a certain number of ammonias. So we're going to replace one or more of those waters by an ammonia. Okay, so you can see the number of waters goes from Y to Y minus N because we bumped out N waters, replace them by N ammonias. Water and ammonia are neutral ligands, so therefore the charge does not change. Okay. Now, if we look at a whole bunch of these stability constants taken from this rather useful website here, it does make me wonder how much of this stuff people study at A-level. I couldn't find it anywhere on any of the A-level specs that we get this detailed on it, but if we do, so be it. We're repeating it for some, but some things can always handle repeating. Okay, so for example, what we're saying here is here's cobalt 2+. We're starting off with it bonded to 6 waters. Okay, and we're replacing it first of all by 1 ammonia, and then a second water by a second ammonia, a third water by a third one, and so on. Okay, and you can see that as we do this, these equilibrium constants decrease. Same thing for nickel 2+. We go from 468 as the equilibrium constant, the stability constant, for replacing that first water. So in other words, the stability constant of the complex that has a nickel with 5 waters and 1 ammonia is 468. 4 waters and 2 ammonias, 132. 3 ammonias and 3 waters, 41, and so on. So you can see that as expected, these values go down. Okay, and if there's nothing else messing around with it, and we're going to talk about things that can mess around with it bit by bit over this movie, nothing messing around with it though, we would expect these successive stability constants to decrease simply because of statistics. Okay, now one immediate mess up comes with silver. You start off with silver and it's actually got 4 waters on it. Replace one of those waters by an ammonia and it's 2090. That's a nice high stability constant. Okay, and that's the formation of this tetrahedral species in which you have 3 waters and 1 ammonia bonded to the silver. Okay, however, the second one, so in other words replacing the second water by another ammonia, we'd expect it to be smaller than about 2000. What's actually found is it's much bigger at 8000. Now this goes against the whole idea of just that statistical replacement of the waters by ammonia, and the reason for this is because the structure changes. You go from having a tetrahedral silver to a much nicer linear silver ammonia complex. Okay, so something we're going to see several times as we go through, a change in what you would expect in terms of the trend of the stability constants is indicative of some significant change happening in the molecule. Now, there's some other factors at work here. Okay, first of all, the metal ion size as we compare one metal to another metal in terms of the stability constants. Generally, as the size goes up, the stability goes down. And if we look at some numbers for EDTA, this is a hexadentate ligand, okay, that's useful, extremely useful for identifying calcium and magnesium. And at some point, you'll do a little experiment associated with that. What we see here is that as we go down the alkali metals from calcium to strontium to barium 2+, the size is going up, but the log of K. Now notice I'm using log of K here, okay, sometimes used just to make big numbers seem more sensible, but we can see that as we go from calcium to strontium to barium, the log of K goes down, which means the K of goes down. In other words, the stability is going down. So all other things being equal, and as we're going through, most of the time you can't say all other things being equal, but all other things being equal, as a metal ion gets bigger, its complexes become less stable. Metal ion charge obviously has a significant effect, okay? As the charge goes up, by and large, the stability goes up. And we can see this again with this EDTA complex as we go from sodium plus to magnesium 2 plus to aluminum 3 plus. So the charge is going up. Well, then the log of the K, the stability constants again, is increasing 1.7 to 8.7 to 16.1. And these again numbers taken from that same RSC website. So some fundamental ideas, okay? All other things being equal, the bigger the ion, the less stable the complex it's going to form, and the more charged the ion, the more stable. And of course, the size doesn't really make a whole lot of sense in a lot of ways, but intuitively you should imagine as the charge goes up, well, then these ligands that are of course electron donors, right? If you remember, we can come back to this again a little bit later on in the talk. Yeah, metals you think of as being Lewis acids, excuse me, okay? The anions you think of as being Lewis bases, and so Lewis acids, they want to accept electrons, Lewis bases are wanting to donate electrons, and the more positive the Lewis acid, the easier it's going to be, the more stable the complexes are going to be. Something that I probably shouldn't mention in this first year, but I'm going to, although we'll come back to it again in the second year, is something called the Irving-Williams series. Put together the Williams in this chap called R.J.P. Williams, a long-time professor of inorganic chemistry, bioinorganic chemistry at Oxford University, true gentleman, one of the great inorganic chemists of all time, really. Never won a Nobel Prize, should have done. You'll find if you look at the history of Nobel Prizes, they're somewhat biased against inorganic chemists. Not quite sure why. It's disgusting. Inorganic chemistry is wonderful stuff. But anyway, R.J.P. Williams, you'll encounter him as you go through different areas, contributed to an awful lot of inorganic chemistry and a true gentleman. Anyway, the Irving-Williams series talks about the relative stability constants of the first row 2+ cations. Okay, all other things being equal, the series goes manganese ions, that's manganese, less stable than iron 2+, less stable than cobalt 2+, less stable than nickel 2+, less stable than copper 2+. In other words, stability increases as you go from left to right, but then goes down again for zinc. So in other words, achieves a maximum at copper. I'll give you some examples of this. First of all, starting off with just replacing one water by an ammonia here. So we've got 5 waters left in ammonia. Again, both ligands neutral. So we start off with the metal 2+ cation. We're going to end up with 2+, charge for the whole complex. As you look down here, cobalt to nickel to copper, cobalt to nickel to copper. The stability constant is going up, but then as you go from copper to zinc, it goes back down again. Look at another series here in which we're replacing 2 waters at a time by these ethylene diamine ligands. Should have put a picture of it here, but there's a picture of these later on. This is 2 nitrogens connected by 2 CH2s, so it's a bidentate ligand. So we replace 6 waters by 3 ethylene diamines, or Ns, or ethane -1, 2 diamine. Okay, knocking off the 6 waters. Using again the log of here the beta, so in other words this is the combined equilibrium constant to knock off all 6 of the waters. So this is the equilibrium constant for this whole equation, right, replacing the 6 waters by the 3 Ns. And you can see again as you go down, manganese less than iron, iron less than cobalt, cobalt less than nickel, nickel just less than copper, but copper bigger than zinc. These numbers, by the way, taken from Inorganic Chemistry by Housecroft and Sharp. This is one of the inorganic books that we like. A lot of your second year stuff is going to be taken from here. I've cherry picked out of it for this year because there's some things that they deal with in a nice way compared to the Chemistry Cubed. But anyway, this is a book that you should get familiar with. These data taken from page 709. So anyway, the Irving-Williams series, again, talking about factors that affect stability constants, all other things being equal. For the first row 2+ cations, you see this nice little series in which the stability increases as you go from left to right. Peaks at copper 2+, goes down for zinc 2+. Now, you might wonder, first of all, why does it peak at copper 2 plus? But then also, when you look at the overall for replacing all 6 waters, the difference between nickel and copper isn't that big. Okay,